In this video, we're going to continue our discussion of how substituents can affect electrophilic aromatic substitution reactions on a benzene ring. In the last video, we saw two examples of activating groups. In this video, we're going to see an example and explain why a group can be deactivating. So, a nitro group is an example of a deactivating group. It makes the electrophilic aromatic substitution reactions slower. Now, the reason the nitro group is deactivating is partly because it's electron withdrawing. Right? We have all these highly electronegative atoms, and so they're going to pull electron density away from the ring. And so it's going to be deactivating by induction effects. But also, when we consider the resonance structures of the nitro group, we end up with a positive charge on the benzene ring. And so that also makes it electron withdrawing because of resonance. So for both reasons, induction and resonance, the nitro group is an electron withdrawing group, so that's going to destabilize the positive sigma complex. And when we talk about deactivating, right, we mean it reacts slower. And in fact, nitrobenzene reacts 100,000 times slower than benzene in the EAS reactions. Now, another difference between the nitro group and the methyl and methoxy groups that we looked at in the last video is that those activating groups were ortho and para-directing, whereas the nitrobenzene is meta-directing. Most of our product is meta. And just like we did with the activating groups, the way we can see where the group is going to add is by looking at the resonance structures of the sigma complex. Okay, so just like we did in the last video, we're going to look at all the resonance structures of the sigma complex that we get when the nitro group attacks in the ortho, the meta, and the para positions. And so when we compare these resonance structures, we've highlighted these two in green for when the nitro adds in the ortho and para positions. These are particularly unstable resonance structures. The reason being, if we remember that in a nitro group, it looks like this. And so in these two green highlighted resonance structures, we have the positive charge in the benzene ring adjacent to the positive charge of the nitro group. And so this is a particularly unstable situation. Resonance structures don't like to have two adjacent charges that are the same sign. We don't like having two positive charges next to each other. So because the ortho and para resonance structures are destabilized due to these two particular resonance contributors, that makes these less stable and less favorable, and so that drives the addition of the nitro group into the meta position that doesn't have one of these really unfavorable resonance contributors. And just like last time, if we were to draw the reaction energy diagrams for the formation of the sigma complexes, the ortho and para transition states and the sigma complexes are destabilized relative to the meta attack, and so the meta is the preferred product. So in general, activating groups are ortho-para directors, and deactivating groups are meta directors.